Okay, so let's talk about the reaction types real quick, and then maybe I'll take you through some examples if I have time. So remember that in the base of this, it's actually very simple. It's the little exceptions and the little caveats that start making it more complex, okay? So the first thing I want you to do is get that first portion where you understand the names. What do the names mean? It's a pure vocab thing, and it makes your life so much easier because you can pretty much figure out the product just from the name, okay? You really, if you just use some logical steps, you can figure out everything from the name, all right? So SN1, what does the S mean? Substitution. So what does substitution mean though? That means something is going to, yep, you are going to switch with something else, right? Okay. So already you know pretty much what the product should look like, right? You should switch with something else, okay? Should you have more bonds? No. Should you have less bonds? No. Cool. That already limits the options a lot, doesn't it? Yeah. Okay, so the next part, N. What does that mean? Nucleophilic, you got it. What does a nucleophile mean? Other way. Remember, philic means wanting, right? A nucleus would be positive. So typically it's going to be something that would have a negative charge on it because it wants something that's positive, right? So this is going to be something that is going to come on to something with a positive charge of some degree, right? And that something that's coming on there is going to be something that would normally have a negative charge, right? Okay. You'll either have a negative charge or a partial negative charge, something electronegative, right? Okay, what does 1 mean then? Yeah, unimolecular. And what does that mean? One molecule, right? So the beginning of this reaction, is it going to have an attacker and something being attacked? No, that's 2, isn't it? So the beginning of this reaction has to start off with one thing by itself, doesn't it? Well, if one thing's reacting and you're not making more bonds, that means it's probably losing it, doesn't it? So the start of an SN1 always has to be, I lose something. Because I'm by myself and I lost something, right? Okay? Is that making some sense? Okay. And then later on, the next step of it, because you don't lose any bonds, you just substitute, right? Means something else has to come in and attack it. Well, if it's losing something and it's going to get attacked by something nucleophilic, that means that it has to become something positive in that first step, doesn't it? So the first step of an SN1, because of, you reason it out, it always has to lose something with a negative charge on it, right? And it always has to gain a positive charge on whatever you're going to have that substitution on. Is that making some sense? The next step always has to be usually a carbocation, right? Something a positive charge, getting attacked by something with a negative charge. Or at least something that would typically have a center of negativity, right? Like a partial negative charge, like a lot of BRs and stuff, right? Okay. Or fluorine, that sort of thing. Water, right? Water has a negative charge on the oxygen. Okay? Okay. What about the SN2 then? Well, the SN2 are the same, aren't they? So we're going to have a substitution. That means we're going to trade one thing for the other, right? It's going to involve a nucleophile. So we have to have some center of negativity, center of negative charge, that comes onto this thing, right? Okay. Well, what's the next part? 2. Well, 1 meant that we started with one thing. It doesn't get attacked by a second thing. It just does its stuff on its own, right? So 2 has to mean what? Something's attacking it. Yeah, something has to attack it. Well, we have a nucleophile, don't we? So what do you think's going to attack it? Nucleophiles are not positive.
Well, no, I'm saying nucleophile is negative, but it's being attacked by something.
Another way. It's a nucleophile that we're talking about. So all of these are going to be nucleophile, right? The nucleophile is doing something. So we're going to get attacked. Something's going to get attacked by a nucleophile. So a negative charge is going to attack some sort of center of positivity. It could just be a partial positive charge on our main chain, right? Okay. How about the E1? So E stands for elimination. Well, what does elimination mean? Yep. Yeah, so we have to eliminate a bond, right? We're going to eliminate some sort of bond. Okay. So we're eliminating a bond. What does a 1 mean? It has to do it to its damn self at first, doesn't it? Yeah. So E1 means that this has to happen on its own at first. It has to start off by itself. Okay? What does E2 then mean? Yep. E2 means it needs to be attacked, doesn't it? So you have something that's going to lose a bond, and it's going to be attacked to do so, right? If we're losing bonds and we don't really have anything saying that we're losing numbers of carbons and stuff, what do those typically mean we have to have before we lose it? These are going to typically happen to things that are like double and triple bonds, right? So you lose a bond because we don't actually have anything that says, hey, we are losing carbons here. Okay? Okay. Or losing oxygens, whatever. Okay. Let's look at some examples, okay? So match the following reaction conditions with the appropriate reaction mechanisms for the, for the alkyl halide given below. Not all bends or mechanisms may contain a condition. Okay, so the first thing you should notice about this is chlorine right here. Okay, so we have these different things. Do we have anything here that looks like it's going to be E? That we're going to lose a bond? Not really, right? Yeah, if any of these things, if we lose the bonds, it's going to give us something completely different, right? Okay. So it wouldn't be as simple as just losing a bond, would it? Okay, so probably not E's, right? We don't really have to worry about those as much. How about the S's? So we look at this. Is there something here that sticks out as being something that maybe could get swapped with and would be stable if it left with some sort of negative charge on it? Which one of those is it? The chlorine, yeah. Yeah. And that's what's referred to as a good leaving group, right? That's what that is. Okay? Okay, so we're going to be sort of looking at things that are going to have 2 factors to them. It's going to need to have some sort of, we're looking at SNs, right? And so we're going to have some sort of, what's the N? Nucleophile. So it's going to have some sort of negative charge center, right? A lot of negative charge centers are going to be things like, well, I mentioned water before, right? So like a good nucleophile is going to have some sort of oxygen probably, right? That'd be something that makes sense. Or it's going to be some sort of salt, right? Okay. Okay. So, by the way, many of the reaction conditions that favor one of these things will favor the other 2. So if it favors SN2, it's going to favor E2 as well, right? Because remember, they both are going to pick off some sort of thing that's okay with being positive, right? And that's how that starts up. And anything that favors SN1 typically is going to go ahead and favor E1 as well, okay? And that's because if, again, it can lose one of those groups on it, then it could lose it in the other one, couldn't it? If it has a very good leaving group, the group could leave. Does that make sense? Okay. If it favors E1, E2, there are going to be a subset of things that could favor E1 and E2, okay? And those reaction conditions are going to involve something that's easily eliminated bonds, okay? Like an acidic proton next to a triple bond or something, okay? That sort of stuff. And then we have favoring SN2 and SN1, okay? Which is, again, a small subset of things. We're going to have something that, well, it's a fairly small subset, okay? Again, it's going to favor, remember that these are going to be acid-base ones, okay? These are going to be leaving groups. So the difference between SN1 and SN2 is going to center around SN1 is going to have really good leaving groups, okay? SN2 is going to have something that can take away an acidic proton, okay? These are acid-base reactions. These are straight up nucleophile reactions with good leaving groups, okay? Does that help at all? Okay. All right, so we look at this right here, NaO, right? Okay, so that's really strong nucleophile, isn't it? Okay, that's going to be your determining factor right there. It's an incredibly strong nucleophile, very strong base. It's going to determine everything about this reaction. Okay? And so that's going to favor an SN2 because it's going to take, it's going to attack, right? We're not going to get a chance to wait around for that chlorine to leave. Okay? This is so powerful, it's just going to attack it and take a proton from it, right? We don't get any time to wait. Or a proton or attack the other side of this. So we could attack this positively charged carbon as well. That would be the SN2. Okay? Okay. KOH, that's a base, isn't it? Okay. And so it's going to be a very good base, isn't it? Right? And so that's going to typically work as an acid-base reaction, right? So again, we're going to have something attacking, and it's going to work as an acid base, right? So it's going to, again, do the attacking. And so we're looking at the twos, aren't we? Okay? So both of these are, again, good acid base, good nucleophiles, very strong ones, negative charges, fairly small and can reach into places. They're going to be attackers, okay? And that's what gives us our twos, okay? Is that they're good attackers. All right. What if we have something that's not very good at attacking? Yeah. Yeah, we have ones, don't we? If they're not very good at attacking, it's going to have that chlorine leave first, isn't it? And then it's going to have to come onto that carbocation, okay? And so that gives us our SN1s, E1s. They're not very good at attacking. They have to wait for those to leave, okay? This, yeah, chlorine is very stable as a negative charge, right? We've seen that a lot. So HCl, was it? Strong electrolyte, right? NaCl, strong electrolyte. Cl minus, it's fine as Cl minus, isn't it? So whenever you see a Cl, that's a very good leaving group, okay? Br is a great leaving group. I minus, great leaving group, right? And so those are really good leaving groups. And so they have a very high chance of being leaving groups, of leaving. Okay? And that happens all the time, by the way, if you're ever curious. Like bonds all the time dissociate, and then typically they're very high energy dissociated, so they just come right back together. Okay? And that's sort of your normal fluctuation between long, short, that sort of stuff. Right? But when you're looking at something that's very stable by itself as a negative charge, then it can break off and spend more time by itself. Okay? Which allows a chance for something that is an electrolyte, or nucleophile, to come in there and react with the positive carbon. Okay? That making a bit of sense? All right, fantastic. So in this case, we just have these two that are fulfilled. All right? So let's look at the SN2 reactions a bit. So we have R3-chloro-2-methylhexane. This may undergo a nucleophilic substitution reaction in the presence of sodium ethoxide. So sodium ethoxide, again, is going to be a sodium on the oxygen. And so it's going to have a very large negative charge, right? And it's going to be small, so it can slip in and attack things. Okay? So we're looking at something that's going to set itself up for an SN2 reaction very readily. And we're told that's an SN2 reaction. Up here, right? Okay. By the way, typically your ethanols and stuff, these are going to be solvents. And you would want something that's fairly similar to what you're reacting with. Okay? So notice ethoxide and ethanol. Ethoxide is the basic form of the ethanol. Did you guys realize that? It's lost in H+. Yeah. Okay, so we complete the mechanism and draw the product of the reaction. So we go ahead and draw these out first, right? Okay. And this one's going to be ionic, so it's going to have a negative charge on the oxygen. That's the ethoxide. Ethyl, 2 carbons. Oxygen, that's the oxide. It has a negative charge, that's the ide part, right? It has a sodium that comes along with it. In solution, that's fine. You can draw like that, but that's what your book would recommend. You could have also left the sodium off, honestly. So anyways, we have our negative charge. That's our nucleophile, isn't it? And SN2 is going to involve an attack, right? Where would we expect to have a positive center on this? Well, we look for the thing that is electrophilic, right? That has a tendency or has a large... Yeah, electronegativity. You got it. So we would look for the thing with a large electronegativity, right? Specifically the leaving group. Something that would be a decent leaving group, right? And yes, exactly, the chlorine, right? It's a good leaving group. It has a higher electronegativity than the carbons. That means the chlorine is going to be slightly negatively charged. The carbon is going to be slightly positive, right? And so that would be our electrophile. Okay? And that's how I identify that. I usually look for the thing that's a good electronegativity, right? Yeah, the good leaving groups, that sort of stuff. Okay, so my negative charge is going to give electrons to my positive charge here, right? Okay. What that means is this is actually going to make a transition state where the chlorine and this oxygen are both bonded to this carbon, okay? And that's the high energy transition state. The chlorine will leave. The oxygen will stay bonded to the carbon. So the chlorine's going to take the electrons in its bond, and that's going to leave as that negative chloride, right? It will go ahead and gather up the sodium and end up being, sodium chloride salt. Okay? By the way, that very likely would fall out of solution, if you're curious, because that would be salt. doesn't dissolve that well in ethanol. But anyways, and that's going to leave you with this oxygen bonded to this carbon. Now, let me ask you a question. So notice this chlorine is coming out towards you, right? Chlorine takes up space, right? So if, like, let's say Calypso here in my front row decides she's going to attack the person in the back row. Can she attack through the person in the middle row? No, that person's in the way, right? So this attacker here cannot attack from the same side the chlorine's on, can it? The chlorine's in the way. So what side does it have to attack from? Behind. And so it's going to end up being behind, right? On the opposite side. So in SN2, always flips your geometry. Okay? Always. It has to. Because it can't attack from the side that had the leaving group on it, right? Okay. Is that making sense so far? Everybody get this okay? Okay, fantastic. Let me know if anybody has any problems, okay? Okay, so the next one is an E2 reaction. So in the presence of sodium methoxide and ethanol, the R3-chloro-2-methylhexane can undergo an elimination reaction as well as the SN2 reaction. Let's complete the reaction mechanism for the major product. So in this case, we're going to be eliminating something, getting a double bond in there, right? So again, I talked about this being an acid-base sort of thing, right? So we're looking for an acid-base reaction. What's an acid-base reaction, by the way? You lose a proton. Something gains a proton. Yeah. So we're going to be losing a proton, right? Okay. So if we're talking about it eliminating this, then it can't be the carbon with my leaving group, can it? Because if it was my carbon with my leaving group, well, that wouldn't eliminate it, would it? That would put a positive charge there and nothing else could happen. We couldn't make a double bond. Double bonds require two carbons, right? So the one it's going to end up attacking is your strong base, which many strong bases, full disclosure, are also strong nucleophiles, and vice versa. But there is a difference between those two terms, okay? You can have a strong base that is not necessarily a strong nucleophile, okay? But yes, most of them are the same thing, because literally an H plus is a nucleus, isn't it? Yeah, so in the most literal sense, yes. Okay, but not all of them are good for attacking a location, right? And so not all of them are great for a nucleophilic addition, attacking a location, okay? Or a nucleophilic substitution. Okay, so we have our strong base slash our strong nucleophile in this case, right? We know we're doing the elimination, right? Need to elimination. And so what we're looking for is we're looking for a reasonably acidic proton. What is a acidic proton? It is something that its conjugate base, the base it makes, is stable. Okay? Okay. It's something that can lose the proton and then would be reasonably stable. So the location we have to attack is going to be, well, we attack the proton, right? That means the electrons from our base go on the proton. The electrons that were with the proton are going to go into a bond, right? Okay. And this bond is going to involve the chlorine. Where would it be most stable to have a positive charge on a carbon? The more substituted carbon, right? Yeah, so the more substituted carbon is going to be the more stable one, okay? And that's actually what you're talking about right here. For the E2 mechanism, the reactivity of the substrate follows the stability of alkene produced. And so the tertiary is more stable than the secondary, which is more stable than the primary. Okay? And that's the rule we're using right there, okay? All right. So we're going to take this proton. We're going to have our electrons that were in the H and C bond go into a double bond between these two carbons. It's going to be the one with the good leaving group because it'll be more stable to have that chlorine come off with its negative charge, right? Okay. And so chlorine will take the electrons that are in the bond. Notice that actually removes any chirality that existed because double bonds don't have chirality. Okay. So yes. All right. That leaves you with OH, because again, H plus, right? That leaves you with NaCl. And finally, that leaves you with a double bond. Okay? Okay. Does that make sense so far? All right. Does anybody have any questions? Oh, we're 2 minutes over. Sorry. I'll still take a question if you want to ask it. But. Okay. If anybody wants to do the rest of these or has any more questions, let me know. We can do some tomorrow or the next day.